So this video is going to be on 7.3C, the last section of 7.3, and we introduce yet another method of finding the volume of a solids of revolution. And this particular method, called the shell method, is useful when you have a hole in the solid of revolution. Okay, so if you take a look at this video, it'll kind of illustrate to you what I mean by a hole in there. Okay. So what you're doing is you've got this planar surface, the purple thing, that's going to be rotated about the y-axis. Okay, so just take a look at this video as it's progressing. And you'll appreciate why you get a hole in there. So the one thing to notice is that in this case the representative rectangles were parallel to the axis of rotation, as compared to in the disk method the representative rectangles were at right angles to the axis of rotation. So now you actually get a better feel for what the solid is going to look like as that area is being rotated by the y-axis. And look, at the end of it, wow, that looks like a kind of nut, right? I guess guys with, well, I wouldn't say guys, don't want to be sexist. People who are hands-on, who are building things and creating things, you probably come across a nut like that. And obviously you need to know what the volume is and so on for whatever engineering applications. I don't know, figure out whether it's going to fit in some space or not. Okay, so that's the topic we're going to study today. Okay, that's the topic we're going to study today. And so if I go back to my notes, what I would like to do actually is I'd like to refer to the textbook, because the diagrams that they have there are really nice. I mean, much better than what I could ever do. So why don't we just study the textbook for a change, okay? So we're going to take a look at the shell method, okay? 7.3, the shell method. And here's a diagram that's really nicely done, and you can see things in there. And since this is right out of your book, I take it that someday you will read it. So you can see why it's called a shell, because right here in the 3D solid that you see, it's a shell. Okay, it's a shell. What's happening here is that you've got this representative rectangle right there, okay, that is rotated about this axis here, as you can see. Okay, it's being rotated like that. And as you rotate it, okay, you're going to get a solid that's really, well, if you want to think about it, a cylinder that's got stuff taken out of it, leaving a thin shell in there, okay? So the book goes in and explains the formulas that you need there, okay? And I suggest that you read that and understand that. What they're doing is they are computing the volume of the inner cylinder and then the outer cylinder, okay, subtracting the two, and so then what you get is that the volume of the shell is really given by this formula here, okay, 2 pi times the average radius, so the average radius would be your P, okay, times the height, okay, which is H, okay, and then the thickness of the shell, which is W, okay. So this is really an important formula, okay. I don't know if you're going to use this specifically in that context, but you will see it being referenced in some other formulas that the book's dealing with, okay. So take a look at what they come up with, and the final formulas are really what's of interest, okay. So the final formulas I'm referring to are these two here, the shell method. I'll come back to it in a minute and kind of talk about it. But let's take a look at an example that they have in there. Okay, and the example is that you've got this triangular region that's rotated about this axis here, okay. Should I snip this? I'll try and snip that. Okay, so this triangular region here, okay, this triangular region here gets rotated about this line here, okay, and this is the solid that gets generated, okay. So it's essentially a cone with a hole in it, okay. And so here's the formula that I mentioned to you earlier, okay, that gets used in here. So what they are saying is that the volume of a shell obtained by just rotating this one rectangle like that, one rectangular region like that, about the blue line there, okay, will create a volume called delta V, and it's given by 2 pi times P of y. P of y is this average radius, okay, times the height of the shell, hy. I know height is not vertical in this case, but that's the terminology that they're using. And then the little width or the thickness of the shell is delta y. So P and H are both functions of y, and we are rotating about some line that's horizontal. Okay, so notice that the representative rectangle is now horizontal, as compared to the disk method where the rectangle was at right angles to the axis of rotation. So one fundamental difference between the disk and the shell method is that the representative rectangle in the disk method is at right angles to the axis of rotation, and it's parallel to the axis of rotation in the shell method. Okay, so once you get that, then you know that you're going to be adding up the little volumes. Okay, add the little volumes up, and lo and behold, you know, we've seen this result many times before, that this guy becomes actually an integral. Okay, becomes an integral. Okay, and so then it's really a matter of a couple of things you need to do in this kind of problem is to find P as a function of y, to find H as a function of y, and then to find the limits of integration. Okay. All right, so that's just the kind of theory. The two formulas that you need to know are right here. Okay, for the shell method. Okay, horizontal axis. So when the axis is horizontal, axis of revolution is horizontal, you're going to be integrating with respect to the y variable. When the axis of revolution is vertical, you're going to be integrating with the x variable. Okay, so again, notice that the representative rectangle shown here is parallel to this axis of rotation, parallel to the axis of rotation. And you really need to burn this image in memory, because really everything is going to depend on seeing these pictures, okay, so that we can apply them, Okay, one more time. Shell method, the representative rectangle is parallel to the axis of rotation. So if the axis of rotation is horizontal, you're going to integrate with the y variable. The axis of rotation is vertical, you're going to integrate with the x variable. Okay. All right, I'm going to move on to an example then. 7.3. And here's an example that I'm going to work on. Okay. So I'm going to pause here for a minute and review the example and then come back to you. All right, so the first example is rotating the region bounded by the curve y equals x minus x cubed and the x-axis between x0 and 1 and about the y-axis. Okay, so here's the picture. Okay, and this is what it looks like. Okay, so we are rotating this yellow region about the y-axis. Okay, about the y-axis. So notice that the representative rectangle is vertical. Okay, it's vertical, and as you can see that you're going to get a hole generated here because the axis of rotation is not along the boundary of the curve. Okay, so you're going to get some funky shape with the hole right in here. Okay, like so. Okay, so let me go snip this guy out. So notice that h sub x, okay, which is this average height here when you think about it, okay, is just given by the y coordinate of the point, that's the middle point of the representative rectangle. So it's going to be given by this. Okay, so h of x is equal to x minus x cubed, and then p of x is just the x coordinate of this point here. That's p of x right there. Okay, so p of x equals x. Okay, and since we are rotating this about the y-axis, the integration variable is going to be x. Okay, so let's go check what we have, and we're going to use the vertical shell method, and the formula for the vertical shell method is 2 pi px hx dx. Okay, we know that px is equal to x, like I showed you in the previous diagram. We know that hx is equal to the height, and that is equal to x minus x cubed. And then after this, it's a question of JDI, except for we need to figure out the limits of integration. Okay, we need to figure out the limits of integration. So the limits of integration are from 0 to 1. Let's go back to our sketch, and we can see that. So x is going from 0 right there to x equals 1 right there. Okay, so that's where our limits of integration come from. So you can see it is really important to graph this thing and really see the picture. Okay, that's where all the work really is graphing this, and then doing this is JDI. Okay, just do it. Okay, just do it. I'm going to pause here for a minute to let you guys finish that. All right, and if you did this correctly, your answer should have been 4 pi over 15. So this is an example straight out of the book that I'd taken, okay? 4 pi over 15. Right, next example. Next example. Horizontal axis of rotation, find the volume, solid of revolution formed by blah, 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 blah. And you're going to use the horizontal shell method, okay? I'm surprised I don't have a picture in here. I guess I better generate one. So hold on. Alright, so the next example I'm going to do is using the shell method, okay, and rotating the region as described in the example right here, okay. And since it's being rotated by the x-axis, we're going to integrate with respect to the y variable, and you're going to use the horizontal shell method formula, okay. Right. Right, so taking a look at what the graph looks like, I'm going to snip this guy out. Close my other snip first. Make sure I'm going. Okay. Alright, so here is the region that I'm rotating. I'm rotating about the x-axis, right, like that. Okay. And so remember from the descriptions that we talked about earlier, or at least we saw in the book earlier, is that PY, since our rectangle is horizontal, okay, PY is the distance of the midpoint of the rectangle from the axis of rotation. So this is PY, okay, and HY is the height of the rectangle, okay. So the curve that we were originally given was x equals e to the minus y squared, and I'll leave it up to you to see how I got that. All right, so what do I want to see here? So I know that at some point here, let's get a black pen. Black gonna work now. Let's do custom. See if that works. Okay. That point there, okay, is a distance x from the y-axis. So hy is actually equal to x. So hy becomes equal to e to the minus y squared. Okay. And then py is just the y coordinate of this point. Right, because remember the y-coordinate is the distance from the x-axis. So our formulation then for the volume becomes this, okay? Py is equal to y, and hy is equal to e minus y squared. And we're almost done. Let's take a look at the limits of integration. Our limits of integration are going to be along the y variable, so they go from x equals 0 to x equals 1. Okay, so those are the limits of our integration. JDI time. JDI. Okay. And so, guys know how to do this integration. Whoops. Let's go do this. Looks like a U sub coming to me here. Okay. Snip this guy out. Did I have the other snip closed? Nope. So snip this guy. I guess, should I be paying Nike this royalty fee, or should they pay me? Because I'm advertising them. Oh well. Okay, so U sub. Uh,